Hi everyone and welcome to today's Tech Showcase. I'm James Raddings, Digital Portfolio Lead here at DCD, and I'm delighted today to be joined by Ronna Davis, who's Chief Revenue Officer over at VoltServer. How are you doing, Ronna? Good to be with you.
Hey, good to see you, James.
Nice. Pleasure to have you. And today I understand we'll be talking about modular power solutions. I know that you've got a presentation for us, so do you want to dive right in and then we've got a bit of time for questions at the end?
Yeah, let's get started. So as James said, I'm Ronna Davis, the Chief Revenue Officer at VoltServer, and today I'm going to talk to you about digital electricity in the data center. If you're new to digital electricity, I'll take a moment to briefly explain our technology, and then I'll walk you through the benefits of using our technology in a data center. We don't have much time together, so I'm going to move fast through the content, but you'll have the slides available for you to review, and if you'd like a more comprehensive presentation, please reach out to me and we'll get that set up. VoltServer is the inventors of fault-managed power. We call our fault-managed power digital electricity. This is how it works. We take power from the utility or your UPS, BESS, or on-site energy source, and we convert that power into a digital packet format. Our patented process is called packet energy transfer. Those packets of energy flow across structured cabling to a receiver that accepts the digital electricity and converts it back into a traditional analog power type to power a local load. Each one of our energy packets includes data for a safety check on the line. We are constantly monitoring the line for any fault or decay, and if a fault is detected, we don't send the next packet of energy. Now, this happens very quickly, in under 4 milliseconds, and it limits the amount of energy into the fault to such a level that it will not cause electrocution or fire. This is what makes our technology safe to interact with and eliminates the need for breakers, arc flash protections, conduits, and lockout-tagout areas. Our transmitter is a solid-state transformer. The technology has been codified under Article 726 of the National Electrical Code, and there is a corresponding UL safety standard, UL 1400. Now, because digital electricity is a digital technology, data is intrinsic to the system. There's no need to add additional systems for monitoring and control. And our API provides a simple integration into other systems like your EMS, BMS, and DSIM. The management platform allows you to set policies and priorities for every single circuit in your facility. Now, in AI data centers, not all real estate is equal. The physical space closest to the AI GPUs, which demands lots of power and lots of cooling, becomes especially valuable. Why? Because that space enables the infrastructure required to support AI, the processors. Now, this graph represents the value of data center real estate from the gray space to the AI server cabinet. To support AI performance, it's critical for us to shrink the footprint of power distribution the closer we get to those AI servers. This frees up valuable space and enables AI data centers to operate at peak compute efficiency. So let's take a look at a standard AC 2N data center lineup. Probably looks pretty familiar to you, right? Now, maybe your lineup varies slightly, but the gray space, typically you would have your main power entrance facility, your UPS, and main switchboard. Sometimes there's a static transfer switch in there. And then in the white space, you have distribution to the floor PDUs, and then from the floor PDUs, you have the busways, busway taps, and the vertical server cabinet PDUs. You have that lineup for both the A and the B sides of the 2N architecture. Now, let's look at a digital electricity lineup. In your gray space, you have your power entrance facility that feeds your UPS transmitter rack. Now, in this case, we're showing 160 kilowatt UPS and 160 kilowatt transmitters, which for comparison, our transmitter would be like the floor PDU in a legacy AC system. From your 160 kilowatt UPS transmitter rack, we have 8 pair 12 to 16 gauge UTP cables in an open basket tray. So it's a pretty small cable bundle. That bundle runs in the basket tray to the server cabinets that are in the white space, where the UTP cables terminate to our high voltage DC PDU. The 350 volt high voltage DC PDU has 4 power sleds. Each can accommodate their own diverse power source. For this example, I am showing a 2N architecture, but our technology can use an optimal N+1 architecture for resiliency. Now, as you can see, digital electricity eliminates a lot of stuff in the data center, and the architecture is considerably simplified. Let's take a closer look at the transmitters and what the wiring looks like on a transmitter. I'm showing you our 40 kilowatt transmitter. It has 16 3 kilowatt channels. We're using 2 8-pair cables for each 40 kilowatt transmitter. So you remember that the 350 volt high voltage DC server PDU has 4 power sleds, right? Well, this diagram demonstrates how you can achieve an N+1 architecture sourcing from 4 unique transmitters for a 100 kilowatt N+1 in only 2 rack units at the server cabinet. So now we're going to look deeper inside. We're going to look at that 100 kilowatt N+1 server cabinet and how that power is distributed to the AI servers. We have 2 PDUs, each with 4 power sleds, and each power sled has 2 high voltage DC power outputs. Each of those outputs supports 2 AI server power supplies with a Y-style power cable. You'll have plenty of space for your power cords, and importantly, you'll also have room to distribute the liquid cooling lines for your GPUs. Now we're going to pan back and look at the gray space in a 4 megawatt, 3 megawatt N+1 edge or enterprise data center. With digital electricity, we will accomplish this with 25 160 kilowatt UPS transmitter cabinets. This requires a square footprint of 234 square feet for both the UPS and the transmitter. Now, if you remember, the transmitter is equivalent to a floor PDU in a traditional lineup. In comparison, a 4 megawatt UPS in a traditional data center would require 236 square feet, and 4 megawatt of floor PDU will require an additional 84 square feet for a total of 320 square feet. It's pretty significant savings at scale. Traditional thinking would lead us to believe that going with bigger UPSs and bigger distribution equipment would save us space, but that's not actually the case. Using smaller modular components in a DE system uses less space, and there is currently, and for the foreseeable future, less supply chain constraints on smaller electrical components. Now, let's head to the white space where the real magic happens. Do you notice immediately the absence of multiple levels of bulky busway and floor PDUs? The slide is pretty empty. But from the gray space, you have open basket tray with those UTP cables feeding each server cabinet that is powered at 100 kilowatts N+1. All that space that you have recaptured from not using busways or having to have floor PDUs can be used to load up more GPUs in your clusters, both up and down and side to side. Additionally, you're going to have space to run your liquid cooling lines. In the compute area, DE can save up to 84% of space over AC systems at these same power levels. So I talked about the 3 components of the system, the building blocks, and we are advancing our roadmap at VoltServer at a breakneck pace and expect to be able to support data center demand beginning in 2026. Now, I don't have time to cover each component, but I do want to point out the increasing power levels in our transmitters and PDUs, the inclusion of an AC power option for cabinets that have low power AC requirements, and finally, the cabling. It's really important. It's also advancing quickly to support data centers, starting with bulk cable that can be field terminated, then moving to pre-terminated cable assemblies and cross-connect hardware. Yes, power will be truly plug and play in the data center for easy moves, adds, and changes that can be done by the same data technician that does your data moves, adds, and changes today. Now, VoltServer is a fault-managed power technology company. All we do every day all day is DE. And we have formed strong partnerships with leading organizations that package our technology, provide complete end-to-end solutions, as well as comprehensive service and support models. So why should you select digital electricity for your next data center? Like all things in life, it's math. DE is the digital transformation of legacy power systems. The digital technology enables the discrete data and management of every single circuit. DE's modularity allows stakeholders to pay as they grow. And the technology scales to support edge data centers to hyperscale data centers, with a reduced footprint that is so critical, especially at the server GPU, for peak compute output. Our unparalleled safety means power can exist in places it can't with traditional power systems, and it will allow for a workforce that can be skilled up quickly to close the significant electrician gap we are facing for years to come. All of these things add up to real economic value for the entire data center ecosystem: the developers, installers, operators, customers, and community constituents. I think we have some time for some questions. James?
Yeah. Thank you very much for that, Ronna. And I've got a soft spot for modular solutions, I must admit. So it's always good to talk about it. It's a really neat system you've got. I wonder, does it support open compute?
Yeah, so it does, sort of indirectly. So we do not have a specific open compute product. However, open compute power supplies, several of them on the market, can take a high voltage DC input. So we can get you high voltage DC to the server cabinet that then can be used to power those open compute power supplies.
And thinking about sort of max voltage, what's the maximum voltage that your system can support? Can it work at, say, 800 volts, for example?
James, that's actually a pretty common question that we get about our solution. And VoltServer operates at 350 volts DC. And the code under the National Electrical Code, Article 726, Class 4 power can operate up to 450 volts DC. Now, the technology itself, digital electricity, can operate at higher voltages and still be touch safe. What we're not sure about is precisely what that voltage range is going to be. We're doing research currently in our labs to determine what that voltage will be. I will say that you'd be surprised at how dense fault managed power can be at that 350 volts DC range. So I challenge you to give it a look. Maybe you can really accomplish your goals at that lower voltage.
Yeah, no, that's great. Well, thank you so much for your time today and coming and showing us the presentation. I know that will be available just for everyone watching at home, just below the screen. And please do reach out to either myself or Ronna if you have any questions on anything that we've discussed today. But that just gives me one last opportunity to thank you so much for being so generous with your time, Ronna, and to VoltServer for sponsoring, and looking forward to hopefully having you back soon.
Yeah, thank you, James. Thank you to the DCD platform. Definitely connect with me on LinkedIn. I'm Ronna Davis. Follow VoltServer on LinkedIn and join our mailing list at www.voltserver.com.